So gas stoichiometry just means that I can use gas laws as an input or an output into the mole bridge. Remember, the core of stoichiometry is using the mole ratio. I'm always going from quantity of one thing to quantity of another thing, right? So I have some amount of a reactant and I want to find an amount of a product, or I have some amount of a reactant and I want to find another amount of a reactant. And so what we can do is we can use gas laws. If I have pressure, volume, temperature, I can use gas laws. So over here, if I have pressure, volume, temperature of the first case, I can find the moles using gas law, right? And then once I have the moles of that, I can find the moles of the other thing using the mole ratio. And then using the gas law and the moles that I found of the other thing, I can find gas properties. Or I could have other inputs. So there's kind of two cases for this. Let's call case one. Case one, I think of it as an easier case or a shortcut. Whenever you see the words STP, STP is an acronym. It stands for standard, temperature, and pressure. And so standard temperature and pressure is defined as 1 atmosphere and 273.15 Kelvin, which is also 0 degrees Celsius and 760 torr, because those are equivalent. If you're at STP, 1 mole of any gas at STP occupies 22.4 liters. This is too many sig figs. So it doesn't matter what gas it is. It could be hydrogen, nitrogen. I chose methanol and sulfur hexafluoride. So 1 mole of hydrogen is 2.02 grams, right? So I could have a really light gas. And for the hydrogen gas, the molecules would be bouncing around very quickly so that they would, at the same pressure and temperature, they would occupy the same volume as the nitrogen gases are heavier. The molecules are heavier, they're going slower at the same temperature. But when they hit, they're going to collide with more force. So, all right. Or ethanol, or 1 mole of sulfur hexafluoride. All of those gases, if we're at STP, have a volume of 22.4 liters, right? Okay, so with that, in case one, we can go from volume and use if we're at STP, we can go directly from volume to moles, right? That's a conversion factor. 1 mole equals 22.4 liters. That's a conversion factor. So if I have the volume, I can go directly to moles, right? And then I can use the mole ratio and I can go to the volume. So let's look at a word problem that I typed up. It says, how many liters of carbon dioxide at STP will be formed from the complete combustion of 82.60 grams of ethanol? And so I have to kind of think of stoichiometry. So I'm not given moles or any, STP is the gas I want to find, not what I'm given. What I'm given is grams of ethanol. So my plan is to go from grams of ethanol to moles of ethanol. For that, I would use the molar mass. That's something we did with stoichiometry or just mole conversions in the past. And then once I have the moles of ethanol, I can use the mole ratio to find moles of carbon dioxide. Once I have moles of carbon dioxide, because I'm at STP, I can use the STP conversion to find the liters. Okay, so like other stoichiometry, before I do anything, I better make sure I have a balanced equation, right? And so I'm giving you the balanced equation, and our interesting players in this are ethanol and carbon dioxide. So if you notice, that's a 1-to-2 ratio. That's our key thing. Technically, we don't care about the oxygen or water. They're just other extra information. So I'm going to break this into steps. So the first step, step 1, is I'm going to use the molar mass. Then step 2, I'm going to use the ratio. Then step 3, I'm going to use the STP. So for step 1, now our molar mass was, let's remind ourselves, is 46.07. I gave that to you earlier. So let's remember that. So, and I have 82.60 grams. I'm just going to write ethanol. That's equal to that. Times 1 mole of ethanol over 46.07 of ethanol. Grams of ethanol cancel, and I would get moles of ethanol. Gives me, and that looks like I have 4 sig figs, so 1.7929, and I'm going to underline the 2 for 4 sig figs, moles of ethanol. Okay, so that's the first step. I like up here, I used the molar mass. I went from grams of ethanol to moles of ethanol. Okay, so the next step is to use the mole ratio. I'm going to use the answer from step 1. I have 1.7929 moles of ethanol. My mole ratio is, if I look at the balanced equation, 1 mole of ethanol to 2 moles of CO2. So I'm just going to take the unrounded value in my calculator, multiply by 2, and I get 3.5858, also 4 sig figs, because the mole ratio is a counting operation. That would be moles of CO2. Let's look at what we've done. So we used the molar mass here to find the moles of ethanol. We use the mole ratio to find the moles of CO2. Now I'm going to use STP to find the liters. I'm going to use the answer from the previous one, 3.5858 moles of CO2. And then my STP conversion is 1 mole of any gas at STP. I'll put STP there just to remind myself. Has a volume of 22.4 liters. So this is probably, you'll get 22.4 on the test. So let's just reduce this to 3 sig figs. So I'm going to take the unrounded value in my calculator, then times 22.4, and I get 80.3 liters of CO2. So this was case 1, and it really depended on being at STP. That was really critical, right? And it's kind of a shortcut. Let's do case 2, which is not at STP. And so if I'm not at STP, let me raise this up here, then I'm going to use the other 3 quantities of pressure, volume, and temperature to find moles using the ideal gas law. That could be my input, and then I would use the mole ratio to find the other quantity, or gas law could be my output. Once I've found moles of the second thing, I could use 2 other quantities plus the moles to find pressure, volume, or temperature.